Hey guys, welcome back to chapter 16. What we're going to talk about today is how do we handle a weak base. So it's going to look very similar to the weak acids. But again, I told you guys that when you have bases, a little red flag should go up because there's always a little wrinkle or a little bit of an extra step. So we're going to dive right into a problem. We've got the basics. We've been practicing the basics. We're going to dive right into a weak base problem. So find the pH of a 0.0015 molar morphine solution. Okay, so morphine, what's that, right? What is the chemical equation for that and how does it break down? Well, a couple tools of the trade, tricks of the trade. So first, I would have to give you a K value for each and every equation. So in this problem, I would have given you, hey, by the way, KB equals 1.6 times 10 to the negative 6. So something to keep an eye on here. Because this subscript is a B, that tells you that whatever this solution is a basic solution. So that's one little trick here to determine the fact that this is going to be a base. You could certainly look up the chemical formula for morphine and then write your equation based on that chemical formula for morphine. A lot of these weak bases, the formulas tend to get really, really big and really, really messy. So what I'm going to use for this problem is I'm just going to use the generic base formula, okay? So I've determined that morphine is in fact a base. So I'm going to call it B for base. That base, just like our acids, is going to be put into a beaker of water in the presence of water. And because it's weak, we know that it's going to be in equilibrium. So a base, remember, is a proton acceptor. Okay, so bases are proton acceptors. So this morphine or this generic B for base here, when it's on the other side, it's going to have that extra hydrogen attached to it. In this case, water is acting as our acid. So if this is a base accepting protons, water must be an acid donating protons. So if H2O gives away a proton, it's going to be left as just hydroxide. Okay, so this is our generic formula for our base. Now we can draw the equation for Kb. So again, it's just the concentration of products over the concentration of reactants. So our products are going to be HB, OH minus. And then again, water is a liquid, not included in our K equation. And then just the bases on the bottom. Okay. Next thing we need to do is we need to draw an ice table. So I'm going to go ahead and clear all my messy writing and put in a nice pretty ice table. So again, the ice table is just going to be the pieces of this equation that we're interested in. Okay. Purpose of this exercise. So eventually we want to determine what is the pH of this. Concentration of the base won't get us there. Concentration of HB won't get us there. But if we can determine the equilibrium concentration of hydroxide, we can take that to hydronium and then to pH. Or we could take it POH to pH. Okay, so again, we are very interested in just one of these items, and that item is the hydroxide. Okay. All right, we are set up for success. Let's start plugging some numbers into our table. So the base solution has a concentration of 0.0015. We're going to assume, since there's no mention of the other two, that they were 0 to begin with. If they were 0 to begin with, there's only one direction for them to go, and that's up. So the change is going to be X and X. And the change for our base is going to go down. There's only one direction. So at equilibrium, we've got 0.0015 minus x, x, and x. Now we need to plug this into our KB equation and solve for x. So KB equals 1.6 times 10 to the negative 6th. And that's the concentration of our products, which is just x and x, over the concentration of our reactants, which is 0.0015 x. Again, x is small is going to be your best friend here. You certainly could use the quadratic if that's your cup of tea. Go right ahead. I'm going to use x is small and then validate it. I think that's a little bit easier. So using x is small, this equation cleans up to 1.6 times 10 to the negative 6 equals x squared over 0.0015. To get the x by itself, I'm going to multiply it by 0.0015. That cancels. Multiply this side by 0.0015. And I get x squared equals. So 1.6 times 10 to the negative 6 multiplied by 0.0015. And we get 2.4 times 10 to the negative 9th. And then to solve for just a single x, we're going to take the square root of both sides. Square root. So I get that x equals 4.89 times 10 to the negative 5th. Last thing we need to do before we can move on is just validate it. So we're going to take that 4.89 times 10 to the negative 5th. We're going to divide it by whatever it would have been subtracted from. So divide it by 0.0015. Multiply by 100 just to make it a percentage. So divided by 0.0015 times 100. And this is 3.26%. So it's valid. Okay, we can use it. All right, so we have a value for x. What's next? Now what do we do? So that x, okay, there's our value for x. That x, remember, is the hydroxide concentration. So the concentration of hydroxide equals 4.9 times 10 to the negative 5th. Now we need to take that from hydroxide concentration to pH. Well, there's two different ways to do this, okay? The first method, we can go from hydroxide concentration to POH to pH. Or we could go hydroxide to hydronium to pH. Again, both are valid, acceptable ways. Find which one is your cup of tea. I'm going to do both with you. So hydroxide to POH, we would take the negative log of the hydroxide concentration. So negative log of 4.89 times 10 to the negative 5th. So POH equals negative log 4.89 times 10 to the negative 5th gives me 4.31. And then pH is just 14 minus POH. So pH equals 14 minus 4.31, and we get 9.69. Okay. Coming on the other side to do this, so to go from hydroxide to hydronium, we would use this guy right here. So Kw equals hydroxide times hydronium, and that's 1.0 times 10 to the negative 14th. So we got 4.89 times 10 to the negative 5th times hydronium equals 1.0 times 10 to the negative 14th. Then I'm going to divide by the 4.89 times 10 to the negative 5th. Those cancel. Divide by 4.89 times 10 to the negative 5th. And we get that the hydronium concentration is 1.0 times 10 to the negative 14th divided by, don't forget parentheses, divided by parentheses 4.89 times 10 to the negative 5th. And we get that the hydronium concentration is 2.04 times 10 to the negative 10th. And then POH is just negative log of that. So negative log equals, and we get the same thing. So 2 ways to solve it. I don't care which way you choose. Find the path that works best for you. But we see that we get the same answer. And then the last thing that we always ask ourselves is, does this make sense? So we decided up front that morphine was a basic solution. It gave us a Kb. And a pH of 9.69 certainly is a basic pH. That's it for this slideshow week basis. I step you through this in a cleaner fashion. What I'm going to do now is I'm just going to post a series of videos working different types of problems. So another example of a weak base, another example of how I can ask a question a little bit differently. So look for that series of videos working with weak acids and weak bases before we move on to our next topic. I hope you guys found this helpful.